This is video 5 for Computer Science 2124. We are talking about linked list operations, and we're trying to be very deliberate about it, aren't we? We're trying to design what each of our member functions has to do and trying to be careful to keep up with the special cases if we can, and we'll see how that works. But it's time for us to get serious about the insert operation, isn't it? Insert, I don't remember what number it was. It's the first real one we're looking at. And rather than worried about the special cases, what if the list is empty and all that stuff right now, let's just dive right into the general case, which, of course, got to start by drawing pictures before. In the general case, since we're going to be enforcing or ensuring all of our class invariants, the head has to always point at the empty head node, which has garbage data in it. And in general, the list is not going to be empty. That's the general case. But we don't know how many nodes, so I'm going to put dots to represent just an arbitrary number of nodes. And then let's say we get down to nodes, I don't know, maybe J here and K next. And even though we haven't looked at how to do it yet, somehow or another this cursor pointer, which is a stand-in for the index number into an array, it's going to be pointing at whatever we think of as the current node in our list. And let's say it points at J. And K points further down the line. Maybe there are other nodes on the list as well. That's enough of a picture, though, for us to get the scenario. And maybe we want to insert data D, for lack of any creativity. D, if we call insert now, the plan is we're going to squeeze node D, a node with data D in it between J and K. And if it seems odd that we would do that, why not make it the new cursor node? Well, think about this. If we're going to make it the new cursor node, then somehow or another we got to get to this node back here. And that's not going to be easy to do in the general case. So what we're going to do is make it easier on ourselves. If the cursor points here, and it's easy to squeeze a node between these two, then hey, I say we go for it. So if that's the before picture, the after picture, head pointer, better be pointed at that empty head node. Don't want to violate those class invariants. Whatever nodes were between that and node J are blissfully undisturbed. The cursor, we'll talk about the cursor after we finish this, but until further notice, let's just say it points at node J. And node D, we put our money where our mouths are. Node D got squeezed in between node J and K. Because there could be other nodes in the list. So here's where we're going. Here's where we want to go. The list was like this in the general case. There's already been a bunch of insertions, moving around, all kind of stuff. But at this point, someone called insert. The main program, whatever the application is, called insert and passed in data D. And our job is going to be to put a new node in the list, dynamically allocated, put it between node J and K. So our job at this point is to somehow or another transform the before picture into the after picture. Now let's discuss some scenarios. And since I'm working with so little board space, some of these you'll need to listen carefully because I'm going to discuss them, but I might not necessarily write all this out on the board. Let's see, what could we do? Since in the after picture, node J points at D, we got to have a node for D, right? So we could just say cursor, arrow, next, this pointer equals new node. And at this point, you got to realize that in cyberspace, nobody can hear you scream. Of course, that's a horrible idea. Why? If we start off by saying cursor, arrow, next equals new node, then poof, K, and everything else becomes this gigantic memory leak if there's a gigantic number of nodes past there. Because as soon as we break this arrow, that's our only connection. Not only to node K, it's our only connection to the rest of this list. So we do not want to break that prematurely. We've got to be very careful and delicate with our little surgery here of the list. But we are going to need, to be able to transform that into that, we are going to need a new node for D. So I'm going to say we've got a new node that we dynamically allocate, And just for safety, I'll put the next pointer to 0, even though we're going to probably copy over that pretty quickly. But I'm going to copy the node data in there as D. So there's my new node. And it can't just be floating around in space. If I'm going to use dynamic memory allocation, I've got a pointer to that somewhere. So I'm going to set up a temporary variable called temp, also for lack of any creativity whatsoever. So I've got a little bitty pointer named temp that points to a big node with D in it. I don't even know what the data type is. I don't care. But now I've got the specific thing that is going to occupy list in the after picture. So how can we do this? We can say now cursor arrow next equals temp. That's exactly what I said before, and it's still completely wrong. Why? Because if I say, I'm going to temporarily mess up my picture. If I say cursor arrow next equals temp, look what I did. That little X there, chop off. There goes all the rest of the list, memory leak. So even though I do want node J to point at node D, I have to be very careful about the order that I do it. How can I keep from losing K? Well, how is K not lost over there? K's not lost over here because node D points at it. And since D is just kind of floating around out in space right now and not pointing at anything, then you know what? Let's make node D, the node that lives at temp, let's make that point at K. So if we could do this, I mean, I told you we'd copy that 0 pretty quickly, and in fact we are. Look what happens there. If we point that to node K first, now we can safely and without risk of memory leak make cursor arrow next point at D. It's the reference count. Right now, at this moment in time, in this temporary sort of walkthrough of what we want our algorithm to do, I've got 2 pointers pointed at node K. So it's safe to break one of them. I'll still have that string that's hanging onto that balloon. I'll still have that down here at node D. So now it will be safe to say cursor arrow next equals temp. And even though it doesn't look like it, this is the after picture. So if we can do these steps and make things happen in the right order, no memory leaks or anything like that, then we're going to be in business. Okay? So now it becomes a matter of translating that into actual code, algorithmic code, which I'll just call steps. Steps. So far, all the algorithms that we've looked at, I think just, what exactly one? The constructor, it only had like 1 or 2 steps. I don't even know if I numbered them. But number 1, I'm going to say short for allocate. Allocate a new node at temp. For data. That's temp. Comments said, stay out of the way of the whiteboard, and I'm trying to do that. That's not easy to do. I'm going to have to step over here temporarily. Temply, if you will. So we'll allocate a new node at temp for the data, and I'm going to assume that, we could do that. Temp equals new node, temp arrow data equals whatever was passed into the insert function, maybe even temp arrow next equals 0, even though now we realize that's not absolutely necessary. So that gets me this far. I've got temp pointed at a new node, and I'll say that I've gone ahead and copied D in it. So that's kind of like a composite step with a couple of things that went on there. Now that I've got that, I need to set temp arrow next to the address of node K. And since this is pseudocode, not actual C++, I'll use the word set. Set temp arrow next. That's this thing right here, this pointer to the next node, set that to K. Except we can't say that. It's not going to be K in the general case. It's going to be some other data. How can we get a hold of this? Well, if we want another pointer to point at node K, where on the board is the pointer to node K? Here it is, right here. It's at cursor arrow next before our algorithm is complete. It starts off, let me go back in time. Here's what we've got so far. Here's what we've got so far. Allocate a new node at temp, check, done that, done and done. Set temp arrow next to something. Well, when we first get here, the before picture, cursor arrow next, pose the address of the node that we want D to point at. So this is going to be to cursor arrow next. Now, let me catch up in my picture. Set temp arrow next. Temp arrow next. Set that to cursor arrow next. We set an arrow, a pointer to a pointer. We end up with 2 pointers pointing to the same thing, which is exactly what we want. Now what? 3. Well, D's hanging on to the rest of the list for us, but somebody's got to hang on to D. So we'll set cursor arrow next to temp. And then we'll have 2 pointers pointing at the node with D. We'll have our temporary pointer where we did our dynamic memory allocation, and we'll also now put D in this chain link of the linked list here. So set cursor arrow next to temp. No growl. No growl. Cursor arrow next to temp. Here's temp. This is the right-hand side. That's the address of node D. So take the address of node D and put that in cursor arrow next. Cursor arrow next. Put the address of node D in there. And again, it's all crooked, but it is the after picture. Cursor points at J, J points at D, D points at K, and voila, that's exactly what we wanted. Now, you might have noticed it's not returning anything. If this is where we stop because we've reached the after picture, it's not returning anything, and there's not really any reason to. Our default is going to be Boolean functions that return true or false based on success or failure, and we'll assume that we're not out of memory on the machine. We'll always be able to get just another little chunk here for a node, so we're not even going to test. We're just going to say, yeah, we can always insert a node on the list. There's always room for one more. What we haven't done that we want to do is think about the special cases, those pesky boundary conditions. They'll get you every time. But first, I haven't said very much about temp. I just kind of pulled that out of nowhere. You know what? The member function can kind of pull that out of nowhere. This temp in green here, that could be a local variable. In fact, that should be a local variable. Do not elevate variables like temp to the status of being a private variable, a state variable. Why not? Because the more of these private variables you've got, the more complicated your code is going to be. Don't make anything a private state variable unless it really deserves to be a private state variable. And how can you tell? What's the litmus test? These have to have values that are preserved between calls to member functions. The main program might be doing stuff. Okay, it's time for me to put a node in the linked list. It calls the insert, goes back to the main program. After it goes back to the main program, we do not want the value of head or the value of cursor to disappear. Each one of those is like a special bookmark inside our linked list object that's keeping up with something that we really need to hang on to. Temp, on the other hand, watch what happens when temp disappears. If temp is a local variable, meaning it's defined right inside the top of the function, it's not up there in private section of the header file, poof. No harm done. That's why it was named temp. It's only a temporary usefulness. It was hanging on to node D until we could get node D situated where it needed to be in the linked list. So after we've got all this in place, temp has outlived its usefulness, and it can drift off into the variable afterworld after the return of the function. So we'll let this come and go automatically, the temp variable, and not again, make it a private variable. Do not do that. Got off the track there just a little bit. But here, let's think about these things. Special cases. What's a special case? Well, what if, and now I'm going to erase this. Take a mental image of that if you need to. What if this list did not have all this stuff? What if the list was empty? So my before and after are gone. I left the steps because what I want to do is, now that I've got what I'll call a working pseudocode algorithm, I want to see whether or not that needs to be adjusted to take care of special cases. Such as, oh no, the list is empty. Well, head is a state variable, and our class invariant, if you remember, our class invariant is head always has to point at the empty node at the front of the list. No choice. Always has to be there. Who's in charge of setting that up? The constructor. The constructor is the one that is charged with making sure that all class invariants are true at the very beginning. We had another class invariant. The cursor. Man, that dried out quickly. The cursor, another private state variable. And we're almost always going to have at least one class invariant that governs the behavior of our state variables, our private variables. The cursor always has to point to some node in the list, but our list is empty. Well, we're using an empty head node, so the cursor itself can also point. So now they both point at the empty head nodes, but for completely different reasons. The head points there so that we don't lose the beginning of the list and have memory leaks and so on. The cursor points there because there's not anything else to point at. So here comes, I'm tired of D. How about E? Let's insert data E in the list. Let's just see what happens. Let's see what happens if we do this. Allocate a new node at temp for data. I'm just going to stick with this color. Sorry about that. Here's my temporary variable again. It popped up when insert was called. Allocate a new node at temp. Done and done. There's the new node for the data, and the data in this case is E. Temp arrow data equals whatever we passed in. And I'm not even going to set that to 0. I'm just going to leave it garbage. It's just an extra unnecessary step. Because here we go. Set temp arrow next to cursor. Whoa, watch out, watch out. Set temp arrow next to cursor arrow next. Cursor arrow next is 0. Take care with 0 pointers. But that's saying copy that 0 from cursor arrow next into temp arrow next. Cursor arrow next is 0. Copy that to temp arrow next. Well, look, got a 0 anyway. Even if I don't do that as just sort of a standard part of my insert function. Set cursor arrow next to temp. Cursor arrow next. This thing, set that equal to temp. Set a pointer to another pointer variable. You get 2 pointer variables pointing at the same thing. Then, when the smoke clears and the function returns, temp disappears. Goodbye, temp. And look at our list. It did insert the first thing in the list. Now then, what we haven't discussed and just came to mind, the cursor, we're using the value of cursor over here, and this is absolutely positively a mutator. Why don't we, after we insert a new node, set cursor to cursor arrow next? So the cursor points to the new node that we just now inserted. We could do that. Here's a rule of thumb, a governing rule of thumb. And as a lazy programmer, I really like this one. Don't do anything you don't have to do. If it's not part of the mission, the goal of insert, which is just to put a new node in the list for crying out loud, if it's not part of its job description to move the cursor around, then don't move the cursor around. Why not? Well, now, if I were to move the cursor, then the only place where I could insert a node again, next time, if I just call insert in a loop or something like that, would be off at the end. And maybe I don't want to do that. Maybe I want these to go between. Maybe I want to insert the next thing between the empty node and E, which is the first real thing in the list. In other words, have the second real node in the list. You know what? This deserves a picture. Let's try it like this. Now, ta-da, a new before picture. We are up to node F, data F. Let's just see what happens. Allocate a new node at temp for data. Here's temp. There we go. There's node F. Set temp next to cursor next. Temp arrow next. Cursor arrow next. So cursor arrow next points at the node that we just got through inserting, node E. So this is going to set temp arrow next to point at node E. Set cursor arrow next to temp. Cursor arrow next is this, the thing we just copied. If we set that to temp, good grief, this is getting complicated already. We barely got anything at all. You know what? To simplify the picture rather than Xing it out, I just now copied over that arrow, so that arrow is gone. It doesn't point at E anymore. And so we're at the end of our function. Steps 1, 2, 3, poof, temp disappears. Where are we now? Look at where we are now. The head points at node F, which points at node E, but that's not necessarily a problem. we're going to see applications for linked lists of all sorts. One of them is a stack, where anything you put in new goes in the front of the list. It's unfair, but there are a lot of applications of stack. Good grief. Your browser history is a stack. If you go from site A to site B to site C and then start hitting the back button, it doesn't go all the way back to site A. If you go site A, site B, site C, then the back button takes you to B. And then the back button from there takes you to A. And then the back button from there takes you to the empty browser. So there's a real quick, fast and nasty example. Sometimes we do want to insert new things at the front all the time. And then when we start taking things out, maybe we want to get them from the front all the time. So there's my argument, as convoluted as it may be, for not changing the cursor unless you really have to as part of this operation. Leave it alone. Now, what if, I'm assuming that that's okay, what if somehow or another, even though we have no mechanism to do that yet, chicken and egg problem, what if the cursor, instead of pointing at the very first node in the list, that empty head node that's just a placeholder, a mere figurehead, what if it points at the last node in the list? That's a special case. You always got to consider the boundary conditions. What if the list is empty? What if it points the first node? What if it points the last node? I think this one might be the last hole to plug up just to make sure that we're not causing any problems here. Let's see. If we insert a new node right now up to G, with the cursor somehow or another moving through the list to point at the last node of the list, is that going to cause a problem? Well, let's just try out our little handy dandy algorithm and update our picture to see what happens. Allocate a new node at temp. Done. Put the data in there. That's for data. I abbreviated it, and now I'm confusing myself. Set temp next to cursor next. Start with cursor next. Cursor arrow next. There's that 0 again. Be careful with those 0 pointers, but I'm copying a 0 into temp arrow next. Temp arrow next. Set cursor next to temp. Cursor arrow next. That's a 0. That doesn't matter. I'm setting it equal to temp, which is the address of the node that has G in it. So it's not going to be a 0 anymore. It will now point at G. And then when we return, temp is a local variable. It disappears. And then we look and see what we have in the picture, and look what happened. Head, the empty figurehead node over here, points at F, points at E, and now E points at G. So let's see, if we were to generalize, if the cursor points at the last node of the list and we call our insert function as it is, then we have a new last node of the list. And yes, there are absolutely occasions where we want to do that. Like, I don't know, maybe waiting list for Big Blue Madness seats or something. If we're implementing a queue, we'll always want to insert at the very end of the list. Good grief, this is a long video. I am going to have to continue this with the next one. So, sorry I kept you late. See you online.